Hi there, you are watching a video of shell and tube heat exchangers for industrial plants. The first question that needs to be addressed is, do this equipment fail under external pressure? After watching this video, it is clear that pressure vessels do fail under external pressure if not adequately designed. A pressure vessel can be subjected to external pressure due to different reasons: an underwater vessel, jacketed vessels, or simply by steam cleaning condensation. The mechanism of external pressure failure is different from internal pressure failure. Therefore, different methods are required to design vessels to handle safely this different failure mechanism. Internal pressure failure can be understood as a vessel failing after stresses in part or a large portion exceeds the material strength. In contrast, during external pressure failure, the vessel can no longer support its shape and suddenly, irreversibly takes on a new lower volume. To verify if the shell of a particular pressure vessel under external pressure is adequate, the verification procedure described in ASME 8, Division 1, paragraph UG 28 to UG 30 must be followed. Observe that the word verify has been used. It means that unlike vessels which are designed for internal pressure alone, there is no single formula or unique design which fits the external pressure condition. In this case, the thickness of the shell is only one part of the design. Other factors which affect the design are the length between supports, the use, size, and spacing of stiffening rings. Shell thickness verification method according to the ASME code section 8 division 1 paragraph UG 28 is long and repetitive. The first step is to estimate a shell thickness that would bear the external load, according to the vessel diameter and support lines distance, of course. Next, the geometric ratios of the vessel must be obtained in order to be able to work with the corresponding charts and therefore obtain coefficients A and B. Once we obtain those coefficients, we are in a position to determine the allowable external pressure. In other words, the amount of external pressure that the vessel can resist. When vessels are designed for both internal and external pressure, it is common practice to first obtain the shell thickness required for the internal pressure condition and then check that thickness for the maximum allowable external pressure. In a pressure vessel under external pressure, support lines are the parts of the vessel counteracting the actions of the external pressure. Depending on the geometry and moment of inertia of the different elements, heads, cones, transitions, etc., these lines will be located in different places. On the screen it can be seen the chart for selection of the factor A. This chart is included in the ASME code part 2, subsection 3. Same as before, this is the chart for selection of factor B, also included in the ASME code. As you can see, the design process is not straightforward, just the opposite. If the amount of external pressure that the vessel can bear is lower than the actual external pressure, the thickness of the vessel has to be increased or the geometry of the vessel changed. Obviously, the diameter and length of the vessel cannot be changed, but the distance between lines of supports can be changed. Increasing the shell thickness to withstand the external pressure requirements won't be always economical. External or internal stiffening rings constitute a very good alternative for the vessel to withstand the external pressure requirements. Shortening the distance between support lines makes the vessel's shell more stable. The simply supported beam is shorter this way, thus more resistant to external loads. With the introduction of stiffeners, another verification method must be followed. Stiffener's verification process is the reverse of the one seen for the shell. It starts calculating the B factor, therefore to obtain factor A from the corresponding table. Ultimately, this method will allow us to compare the moment of inertia required with the moment of inertia available. If the available inertia in the vessel is not enough, bigger and/or more stiffeners shall be adopted. As mentioned before, design of stiffeners themselves is a trial and error procedure. So, where to start? How many stiffeners to add? Well, something to bear in mind is the distance between stiffeners. Even when the size of the stiffener rings have been estimated, where should they be placed? For this particular exercise, please see the study notes. Or, for example, the shape of the stiffener. If possible, standard profiles should be used. They are generally cheaper and the manufacturing process requires a lot less man-hours. And at last, the position of stiffeners is very important. Locating rings over circumferential weld seams shall be avoided when possible. As a conclusion, it is important to mention the following. When vessels are designed for both internal and external pressure, it is common practice to first obtain the shell thickness required for the internal pressure condition, and then check that thickness for the maximum allowable external pressure. If the design is not adequate, then a decision is made to either increase the shell thickness to the next commercial plate thickness available, or add stiffening rings to reduce the L dimension, distance between support lines. It is worth mentioning that neither increasing the shell thickness to remove stiffening rings nor using the thinnest shell with the maximum number of stiffening rings is economical. The optimum solution lies somewhere between these two extremes. The different elements of a pressure vessel must also be verified against external pressure. For all these elements, cones, transitions, etc., provisions are made in the ASME Code Section 8, Division 1, Paragraph UG 33.